So, welcome to lecture 14th on stability of structure. So, let us briefly recapitulate what we are doing. So, we are discussing buckling of plate, and in the previous class we have shown that buckling, while considering buckling of plate, basically you have to consider its equilibrium in deformed configuration, perturbed configuration. But what we have seen that the out of plane, that means the equilibrium in the z direction, we consider same as whatever we use in bending of plate, right. So, that means whatever little deviations that may occur because of the deformed configuration, okay, on the vertical equilibrium equation, that the force equilibrium equation along vertical z direction, that we do not basically consider. However, the contribution of the in-plane forces because of the deformed configuration has been taken into account, okay. And that is what we derive the governing equation d nabla square wx y is equal to nx due to w dx2 to nxy due to w x del y plus a and y due to w dy2, and then from there. So, this is the additional term that is coming by considering the deformed configuration of the plate, whether this is the same as the equation from the beam bending, right. And then for the as far as buckling is concerned, nx, ny all these forces are assumed to be constant over the plate, right, they do not vary. That is strictly valid for the buckling, pre-buckling regime, okay. Now, then we have considered a simple example to solve. We have considered a simply supported plate, okay, with the governing and which is subjected to uniaxial forces, uniaxial compressive forces, stresses, and then we solve it, and we have seen that this result into eigenvalue problem as earlier. We have solved the trigonometric eigenvalue problem. We assume some double Fourier series, involving sine functions, and by satisfying the boundary condition, and the boundary condition for simply supported plate we have derived. We have seen that at each end, like x is equal to 0, x is equal to a, w is equal to 0, that is vertical deflection is 0, and then the bending moment is 0, that ultimately condensed out to be d2w dx2 is 0 of these two end, and then other end d2w dy2 is 0. So, all this therefore, so on each face there are two sets of boundary conditions, right. And we have solved this thing. So, this is one approach to solve, and then we have also seen that physically the behavior. So, we have assumed, for the simplicity, we have assumed that, well, there is only one, only single wave, sine wave prevail, this only single sine wave is there in the y direction, and the other direction we have allowed multiple waves, okay. So, then we are restricted to this is one kind of simplification, right. So, then we have seen that depending on we have minimized. So, nx is the critical, okay, axial, the critical value of the axial compression. So, then we have minimized, and then we have seen that, well, depending on the aspect ratio a by b, from one mode it shifts into different mode, right, okay. And then the minimum critical load is if you can recall, n critical along x was pi square d by v square, k pi square d by k, it was 4, I think, okay. So, from one mode to so as we are changing a by b ratio, when a by b ratio appears in integer, that means it can form a perfect square, then the critical load attains minimum. Otherwise, there is a little increase in both sides, okay, whether a by b is less than n integer or a greater than some particular integer, okay. And with increasing aspect ratio, there is mode shifting occurs from the first mode to second mode to third mode to third mode, and then when the shifting is occurring, that shifts. So, if you see the curve, with changing aspect ratio, the increase in the critical load, that follows. So, the boundary follows like a tongue kind of structure, which is referred as Arnold tongue, and which is a very general kind of structure that you not only in buckling of plate, but you observe in many other scenarios, especially in dynamical system and others, non-linear dynamics. So, all these things we have done. Okay, we have also seen that we can study the biaxial bending, buckling of plate under biaxial compression. Okay, where it is subjected to both Nx and Ny. We can simplify this equation for solving by treating Nx and Ny to appear in constant ratio. So, that means R is equal to Nx divided by Ny. All these things we do not consider that, but now what we are going to do, we are going to focus on two things. See, you are all, so whatever I am now going to discuss, this you have learned perhaps in your plate theory of plate, but once again I would like to emphasize it. See, we know the boundary condition float plate, bending or buckling here is either it is simply supported, that is what we have learned, W is equal to 0, d2W dx2 is equal to 0, or d2W dy2 is equal to 0. Now, it can be fixed. If it is fixed, like for example, if I am having this end fixed, so over this end x is equal to 0, so what will be the boundary condition? Boundary condition will be W is equal to 0 and the slope is 0. So, del W, if this is x, del W del x is equal to 0, right? This is the boundary condition. So, as far as pre-boundary condition, simply supported or constant, you are all done, right? Fixed. This is fixed boundary condition, but what about free? Free edge. So, for free edge, there is a little problem that I would like to quickly, many of you might be aware about that. So, I am considering that, I am assuming that this and these edges are free edge, okay, free edge. On free edge, what will happen? On free edge, on free edge basically, see, the bending moment is 0, the shear force is 0, as well as the twisting moment is also 0, right? So, bending moment x is 0, twisting moment to be 0, and Qx also to be 0. But how many boundary conditions is permissible on any edge? Only two boundaries. So, these are three boundary conditions, right? But only two are permitted, right? But only two boundary conditions, are permitted. Because the order of the differential equations, right, is fourth order differential equation, right? So, what will you do? You have to somehow condense these three boundary conditions into two. So, these three boundary conditions, this was identified by Poisson, right, and it was modified by Kirchhoff from 3 to 2. So, how will that will do? That I am going to show. So, if please see that what is Qx? There is a relation, the Qx del mx del x plus del m xy del y, Qx, right? Now, this one mx, that is what I am going to do something. What I am going to do, I am assuming that this is so this is x, this is y, okay. So, on this, I am considering this, so when it is along y, okay. Now, when it is subject to mxy, maybe it is a mxy means, I can consider that within a small stage mxy is the twisting moment per unit length. So, by the stretch of dx, the twisting is how much? mxy into dy, isn't it? mxy into dy, right? So, may I replace it with two forces which are a distance dy apart? Can we do that? as the equivalent shear dy, right? Now over y, this is changing. So once again, now we can also do it, over next length, we also replace it with this is mx plus del mx y del y into dy. So, this is changing. So, over a length of dy, this force is going to change. This will increase, right? Now, you consider, so, or this segment, over a segment dy, there is an unbalanced force, right? This force is unbalanced force. So, this, the unbalanced shear is how much? Shear is del mxy ay into dy, and this is over a length of dy. So, per unit length, the unbalanced shear can we express is dmx by dy. You understand what over this length, mxy is the twisting moment. So, this is increasing if you use a positive x direction, right? So, over a length of dy, I can replace the twisting moment mxy dy as a two shear forces distance dy apart. Now, for the next segment, I can also replace it with the two segment, this and this, right? Now, for one segment over this, take half of this, take half of this. So, there is an unbalanced force, right? Because this is not balanced by this, because here, the twisting moment is going to increase over the length, over the segment, right? Over the length, over increasing y, right? So, that unbalanced shear is how much? This is mx and this is mx plus. So, this one is the unbalanced one because upward, downward, right? I am not considering that much. I am not strict about the sign, etc. But you understand there is an unbalanced shear, right? So, may I replace this twisting moment with the equivalent shear? May I replace this twisting moment with an equivalent shear? So, what is the equivalent shear? So, replace the twisting moment with an equivalent shear, equivalent shear, and that is what is magnitude del y, right? So, earlier it was qx and now this is additional. So, total shear now. So, both. So, total shear now del mx del x plus del mxy dy plus del mxy dy. So, del mx del x plus 2 del mxy dy. This is the total shear. So, now do you understand? So, now these two we can combine. So, from 3 the boundary conditions is mx, this is an independent boundary condition and these two are combining into one. So, this shear is called Kirchhoff shear, okay. This shear is called Kirchhoff shear, okay. And then we can simplify it by substitute, okay. So, you just substitute, so it is minus d, d2w dx2 . So, you will see that this, if you simplify, you will see that d3w dx3 2 minus nu d3w del x del y2. Look, ultimately you have to express in terms of the displacement, because we have formulated everything in terms of displacement, right. So, displacement order condition. So, total shear is this, and for the free edge, so for the free edge, So for free edge, so at free edge, make this one to be 0, huh? d3w dx3 plus 2 minus nu d3w del x d3 del x del y2, right? Bending moment you take separately, okay? So do you see how these two has combined into one? So this kind of simplification has been proposed by Kirchhoff. Poisson identified the boundary condition and then the anomaly over there, that while there is some mismatch, okay? In order to bring consistency, you have to condense out these two boundary conditions into one, and that was solved by Kirchhoff, okay? And this is called Kirchhoff's shear. Clear? And then Mx, the way you will here in the free, here bending moment, of course, you want to convert into displacement. Of course, this will give another equation, d2v del x2 plus d2, fine, right? But yes, this boundary condition is a little complicated, so you cannot just intuitively, it is difficult to assume some kind of specific form, okay, sine. So that's what, nevertheless, it can be solved using, of course, you require a digital computer, you require a computer, and you can use some, more terms in the Fourier series, and then you minimize both the both the error in the equation as well as error in the boundary, okay. So it can be done, that's not a problem, okay. Similarly, the way you have physics, let me explain first. So the way you have if you solve it, then you will get the critical load to be, the expression, let me write it down. So nxy, then critical nxy, this is k pi square d upon s square, okay. Well, b upon b square, okay, b square, and this k is nothing but pi square by 32 beta into lambda, where beta is the aspect ratio a by b, and lambda is well, anyway. So what I'm trying to say, that it can be expressed as something into pi square d by b square, okay. No k value, so I am just going to plot it over here, okay. So when I am plotting it, I am assuming this is 1.0, 1.5, 2, 0, 2.5, 3, So, when see we want to demonstrate the similar structure as previously, how the mode shifting occurs. Okay. So, this here it is nothing but A by B ratio. A by B ratio is the aspect ratio. So, you see when the A by B is less than 2 or 2.05, then so for all this mode you are basically plotting the how this K, this is nothing but K, and this is for different aspect ratio A by B. Okay. So, K versus this. So, this is for the one mode, this is the first fundamental buckling mode. Okay, this one. So, first buckling mode is what you can see that this will consist of only one buckling lobe, right? Only one buckling lobe. Okay, and this is of course kind of a symmetric buckling. Symmetric, one lobe means one, has to be symmetric. Then the second mode is antisymmetric, because if there is two lobe, this must need to be antisymmetric. One will come out, another will go down, right? Then it is two large buckle, it will, and then symmetric three large buckle, it will. So, what we see that how this buckle will look like, that let me explain to you. Okay. So, if I draw a contour, then it will look like this. That means, maybe this is value of 1, then this is 0.8, 0.7, 0.6, something like upward. So, it will come, it is coming out. You see that it is coming out, but then the contour looks like this, it is being flattened outside. So, here it is maximum, all this, other places it is going down. You understand the surface? Now, why it is little oblate, why it is shrinked in this direction? That is because under shear, if it is subjected to shear shear, that one diagonal will be in tension, another diagonal will be in compression, right? So, this side it is subject to tension, so some tension stiffening is occurring. That is what it is basically reducing the extent of this outward deflection. You understand what I am trying to say? On the other hand, in the other direction it is compression, so it is more susceptible to buckling. Sure, that is what basically when you buckle under shear, what happens is that one diagonal is under tension, another one under compression, and they are mutually perpendicular to each other, right? So, it will be shrinking along one, whether it will have little extension on the other direction. You see, that is what essential. So, this is a symmetric buckling, because it is symmetric, right? So, this is the fundamental or symmetric mode, fundamental or and symmetric mode, symmetric with single buckling lobe, with single out of deflection lobe, okay. And essentially that is what is happening where? Now, this one, you see that, and fundamental is the we will give the lowest load. Of course, K is starting from 9, it is going down, with increasing aspect ratio it is reducing. That see here this is little different. The difference you must understand from the uniaxial buckling to shear buckling. In uniaxial buckling it was diminishing, but then it will going up, it will go up depending on the A by B ratio. When A by B ratio is being an integer, that means it can perfectly accommodate the square shape, then it will attain lower value. Otherwise, in both directions, both increasing or decreasing A by B ratio, aspect ratio from an integer, it will both the side it will increase. That is what this will form this kind of Arnold tongue kind of structure. Here it is not. Of course, here also Arnold tongue will be there, because from here you see here, from here you see that, from here, then here, yeah, these are also, this is one Arnold tongue, this is another Arnold tongue, you understand? But it is little different, it is not monotonous. In this case it is kind of decreasing mostly, you see that? And then these are the point of transition, mode transition. Nevertheless, mode transition is akin to the same behavior, akin to the behavior as we see in the under uniaxial compression, you see, but the trend is different. So, then as soon as it is crossing 2.05, then there is a mode shifting, it is going to antisymmetric mode is being energetically favorable. So it will try to buckle in antisymmetric. So there is a mode shifting occurring for symmetric mode to antisymmetric mode, right? Then you further increase around little 3.5 or so, it will go to another symmetric mode, that is consisting of 3 buckling lobe. Let me draw it, how it look like. You see, so this is maybe 1, this is 0.8, this is 0.7 or something like that, and maybe this is 1, this is 0.8, 0.7, something like that. So you see that these are all negative, okay. So there is a ridge over which it is distinguishing between positive out of plane deflection and negative out of plane deflection. So this fellow is coming out and this fellow is going up. You have learned these kind of things while studying warping torsion, right? When you solve the Poisson's equation, you will get the warping functions, and then from there you will plot. You have plotted that. So here, so aspect ratio is around 2. So this fellow is going up, this fellow is going down. Once again, this little oblate shape is because of the tensile stiffening along the other diagonal direction. Okay, you see. Similarly, now, so this consists of, this is second mode, and this is an antisymmetric mode. This is antisymmetric mode. This is positive, this is negative, right? And it is having 2 buckling lobe, right? Now you can go to the third. You can go to the third one, where then one fellow will go down, other 2 will come up. Okay, when the aspect ratio is little larger than 3. So then it will, this will be the go. So shifting is indicated 1. These are the Arnold's tongue. Okay, Arnold tongue. Arnold tongue. So qualitative similarity you understand between the uniaxial buckling and then the shear buckling, right? There are qualitative match, but yes, the behavior are different. Okay. Now we will see, we will pave the way how we will do the energy analysis. Okay. So for energy analysis, that is most convenient, right? That's what we have done in our all the analysis previously, whatever we have done. So we will try to find out the energy expression for the plate bending. So you have done the energy expression for the plate bending, perhaps plate bending theory. So energy approach. So strain energy of bending of course, what you have learned in our for the beam moment, and which one is energy conjugate to moment, curvature, moment into curvature, that will give you the strain energy, right? EI by 2 d2w dx2 square dx, right, or m square dx by 2 EI. What is that? From where it is coming? Bending moment into curvature, m multiplied d2w dx2, right? So here we have 2 bending moment, 1 torsional moment, right? So respective curvature term we should multiply, okay, and don't care about the sign. moment multiplies the curvature. Okay. Now you substitute the equation. So if you substitute, so then mx, you know, this all this mx is take and substitute, and then you simplify. If you simplify, then you will get the final expression. I am not doing the simplification. You take some, everything we express in terms of displacement, because it is intuitive to assume the displacement field using some kind of approximation function. Okay, that's what the way you do for final, for you know, Galerkin method and other things, Rayleigh series. Okay, that's what. So d by 2 integration, you know, that is the expression for the strain energy of bending. Okay, plate bending. Huh? So we have this expression ready, and now we must find out the expression for the work done. Okay. So now work done ordered by the influent forces, right? So work done by the influent forces due to out of plane deformation, right? So Nx, what is the respective, you know, respective you know, in plane deformation because of out of plane deflection, you have to integrate the von Karman nonlinear term. Epsilon xx is what? Half del w del x square, right? So half del w del x square. Of course, when you are integrating, you will get the, you know, axial deformation, right? So this one, huh? Please note that the in plane strain is because of the out of plane deformation only, right? We are not considering, there is no in plane deformation, no u, no v, only w. Similarly, you will have ny up. This is for ny, right? And then we can have nxy. So for the nxy, you see that it will be half del w del x del w del y, and for nyx it will also have del w del x del w del y. So please note that there is in, you know, this is half term, and then both of half, if we sum it up, then, you know, this is from where this is coming, you know, you can consider this epsilon ij is what? U I comma j plus u j comma I half, right? Half. plus then of course uk comma I, uk comma j, right? So k comma I, k comma j means w del w del okay. So if you want to, I mean, I can solve a very small, So now for shear buckling, let us solve an illustrative example. Example for shear buckling, right? Example. So we are given a plate, subjected to shear, pure shear. So when we do shear buckling, then how the expression will look like? So please note it down, and then I will write it down. Okay. So strain energy is bending. The expression we have already derived. D by 2. It was d2w x2 d2w by 2 square plus 2 1 minus 0. d2w del x del y square minus d2w del x2 del 2w del y2 dx dy ub, and then for the work done only of course integrating over the area, only shear one is no del w del x del w del y. Now for the way we do it, so you just the potential energy is strain energy minus work done, right? We assume some w for the shear reflex. So we assume w to be, see, if we want to include more term it's fine, but then if we include too many terms, we cannot do the hand calculation. It will be too complicated. Of course, if you are using a computer, then you can include as many terms as you want, right? And nowadays with symbolic computation in Maple or Mathematica, you can do very simple this carrying out this integration and others, right? So here I am writing q1 sin pi x by a sin pi y upon b. Two term approximation I am doing, okay? Sin 2 pi x upon a sin 2 pi y upon b. Please note that I should have also included q3 sin pi x by a sin 2 pi by y and q4 sin 2 pi x by sin pi y, because you see this is pi x by a pi y by single wave and this is double wave, but cross between single and double should have also included, right? But even with this thing you will get reasonably good approximation. So if you substitute here and if I write down the express, carry out the integration over the domain ex dy, okay, and then you will see that expression looks like pi to the power 4 by 8 ab dab 1 by square plus 1 by b square q1 square plus 16 q2 square plus 32 by 9 nxy q1 q2, this way with the expression on integrating, okay. You see that everything in terms of generalized coordinate q1 and q2, right? Now you do minimization of energy, del pi del q1 is equal to 0, del pi del q2 is equal to 0, and then in the first equation you will get pi to the power 4 upon 4 dab 1 by square plus 1 by b square q1 minus 32 by 9 nxy 0. nxy plus 4 to the power 4 d ab 1 by square plus 1 by v square q2 0. You see that both a homogeneous systemic equation, it's basically give rise to a eigenvalue problem, right? So when we are approximating using this trigonometric function, so this is some kind of numerical, technique to, I mean essentially doing error minimization while fitting. So a trigonometric eigenvalue problem is being converted into a algebraic eigenvalue problem. So you see there is q1, q2, so make the determinant to be 0, and so this eigenvalue problem, the determinant must be 0. So on solving this, a characteristic equation on solving, and then you will get nxy critical 9 by 32 y to the power 4 d ab 1 by square plus 1 by b square square. So that is the critical. So you see that one estimate of the critical load you are getting by doing so, and the respective mode shape you have already predetermined, right? So single lobe, and then for both the, you have to find out the value of q1 and q2, and then you have to substitute, and then you have to plot the eigenvectors, and then you plot it, and you will get a surface. So you will first mode, second mode, of course here also you will see that you will get it, first mode will be the symmetric, and second mode, substitute and see what you get, because from the algebraic eigenvalue problem the eigenvector will give a relative value of q1, q2. So positive, first maybe first eigenvector both will be positive, and the second one will be one will positive and the negative, okay. So then some asymmetry will be there in the second mode, maybe you will check it, okay, I don't know. So this is of course simplest approach to solve, given the fact that the integral of the standard integral in terms of this sinusoidal function, you can directly substitute and do it. But yes, of course, if you want to include more term, then you have to do take help of a computer program, okay. But nevertheless, this expression is not very bad approximation. It's a reasonably well approximation of the actual or exact load, okay. So where do you see shear buckling? Could you please give me some example? Where do you see shear buckling? Of course, one example is that shear buckling is very common, that we all came across in while designing our plate girder, right? Plate girder has very long web, right? So those are susceptible to shear buckling. And if you can recall that in steel design there is a provision that while if V by Vd, the shear force that is coming, and design shear strength is less than or equal to 0.6, but that is for different reason. That the two cases for the design of beam, steel beam, one case if V by Vd is less than or equal to 0.6, another is something greater than 0.6, that is something different. That is because of the influence of shear deformation. Because if the shear is little too high, then it will affect the behavior. There will be significant shear deformation, and that you have to take into account, that one. But there is another provision what we need to satisfy for the design of plate buckling, plate design of plate girder, that you have to check for the shear buckling, okay. So that is one example. But there you will see more common example, shear buckling is also exploited, for as a sacrificial device, of the energy dissipation device in for the seismic resistant structure. Okay, those of you who are working with Professor Durgesh Rai group, you will see that he has developed the Shear yield panel. Still that Shear yield panel. So you will see that that is aluminum. So aluminum was the material that was used, but in order the common aluminum, we have aluminum they have taken, and then they do annealing on aluminum. Do annealing, that it reduces, there are some crystal reorientation microstructural thing happens. It reduces its yield strength. Okay. So when it reduces yield strength, and then you will see that there are stiffeners. If you go to structural engineering lab, you will see those Shear yield panel. Okay. So and then you install it in building. Okay. You will see that the way it was installed, consider that there is a bay. Okay. So maybe this is concentric braces will be there. Okay. And there this Shear yield panel is there. Okay. So, when it is subjected to lateral loading, cyclic loading, then what will happen? This fellow will be subjected to shear loading, right? Isn't it? And under shear loading, if it has low yield strength, then it will yield, and if it yields, then it will dissipate energy. Of course, there it is not the monotonous loading, it is cyclic loading, and because it is cyclic loading, you will see that it dissipate energy. Okay. Something like that. So, the area under the loop will give, so this is the hysteresis loop, that is what you will see there. Okay. So, the area under the loop, in each cycle it is dissipating energy. So, that so basically help in dissipating input energy coming up from seismic excitation. So, it is a control device, passive control device. Okay. Now, interesting thing is that you have to prevent, in order to, you are all doing the experimental method, right, course, right? Did you do that experiment, inelastic buckling of brace? Inelastic buckling of brace? You have not done, it will come. So, you will see that for the inelastic buckling of brace, if you just take a simple brace and then you allow it to buckle inelastically, on tension it will definitely do, okay, but on compression it will come and then it will go once again. Why it is not able to come? Because it is buckling prematurely. It is buckling prematurely. So, if it buckles prematurely, it is a geometric instability. It is not allowing it to mobilize its full strength through yielding. So, that is what, in order to for optimal use, you have to design it, you have to provide stiffener etc., so that it does not buckle prematurely, plate buckle. So, aluminum plate buckling, of course, is inelastic buckling, between yielding will precede the buckling. So, it is inelastic buckling, and there are formulas given by Goddard and others that they use. But this is one example of shear buckling. Why shear buckling is utilized, not buckling is utilized, but the yielding is utilized, and then you have to make sure that it does not buckle prematurely under shear. Okay. So, now we are going to consider post critical behavior. So, why we have considered, so you see the way we are progressing over the course, we have considered very simple example, twice example, and 4 different system, which represent 4 classes of instability behavior, right? We have considered, critical load and then post critical behavior, whether it is stable, unstable, or imperfection sensitive or things like that, right? Modal interactions and things like that, right? Now, we have demonstrated those simple behavior that was demonstrated by E-shaft toy system into one practical example. We have considered the buckling of column and we have considered the post buckling of column. We have seen that column does not have any significant post buckling strength. Even if the end rotation is 30 degree, it is only 3 to 4% increase in post critical capacity. So, essentially for the column, as soon as it buckle, it depletes all its load carrying capacity. That is not so in plate. So plate has some interesting behavior. Plate has significant post-critical strength. Even if plate buckle, it doesn't lose its capacity to carry load, and that is utilized, that is exploited even in code, in design, and then code stipulation is made accordingly to exploit that. So that's what we will see, that what is the mechanism, what is the science behind that. Okay. So post critical behavior of plate. Now we have seen the governing equation for the plate buckling, that is D another 5 minutes, right? So we have seen this equation we have utilized for the plate buckling, right? And here we have assumed that Nx, Ny or Nxy, they are constant, okay? Constant across the plate, huh? They remains identical across. So there is no variation of Nx, Ny and Nxy for the buck, and then that's what we have find out the critical value of Nx, Ny, Nxy, right? But as soon as a plate buckle, what will happen? This Nx, Ny and Nxy will no more remain constant across over the plate. They will redistribute. And why it redistribute? Because in column there is no provision for redistribution because it is one dimensional, but in plate is two dimensional. So there are provisions of redistribution. However, two dimensional doesn't mean that always it will redistribute. In cell there is nothing like this. But in plate, it can redistribute. That means Nx, Ny and Nxy can vary over the plate. You see that domain. So that is the first thing. So Nx, Ny and Nxy is no more constant. These fellows are no more constant. So they vary. So the in-plane forces, in a plate vary after beyond yielding, after buckling. Once it buckle, then it started redistributing. Okay, the reinforcement in the plate varies. Okay, they start redistributing. Okay, they start redistributing. So if they start redistribution, then of course you have to enforce that the equilibrium is maintained. So this require, for this region, the equilibrium of in-plane forces must be considered. The equilibrium of the in-plane forces must be considered for post-critical behavior, post-critical analysis of plate. Did you understand what we try to mean, right? We need to consider the in-plane equilibrium. See, this essentially, this is nothing but equilibrium equation along the out of plane direction. That means along z axis, vertical direction, right? In-plane forces, equilibrium of in-plane forces never arises because if Nx, Ny, Nxy are constant, right, they are always in equilibrium, right? In both the direction they are under compression, right? But even though when you with the plate buckle, at the end it is always Nx. In global sense, Nx and Ny are always maintained. These Nx and these two need to be same, right? P, right? They are compressed. But inside the plate, away from the plate boundary, the in-plane forces get redistributed. So, a point which is away from the boundary, the in-plane, the equilibrium of the forces along the in-plane direction must be taken into account. So, that is the prime difference, and then the main difference from the buckling analysis or critical analysis and then the post-critical analysis. And here it will portray significantly different interesting behavior. That we are going to explore. Okay? Okay, next class we will do. Thank you.